Hi, my name is Viviane Moreira. I'm an associate professor at the Institute of Informatics at URGS, and I'm going to talk to you a little about a collaboration project we have with SEMPES Petrobras and PUC-RS. Our project is entitled GeoDigital Integrated Search for Heterogeneous Geoscientific Data. Our main motivation is that exploration and production data management specialists agree that the most valuable information for an organization is represented in the form of unstructured data. Reports, articles, emails, images, and diagrams are examples of unstructured data. A McKinsey report estimates that employees spend almost 10 hours a week searching and gathering information. So, what we hope to do is to address this issue and try and reduce this search and gathering time. The general goal of our project is to provide a solution for multimodal information retrieval that is able to handle heterogeneous geoscientific data. Multimodal information retrieval is the process of organizing and enabling search for different types of data, which are the modalities. It can be text, images, audio, video, 3D models. Here, our focus is on unstructured text and figures. Our approach combines different areas from computing science, including information retrieval, image processing, machine learning, ontologies, natural language processing, organic archivology, human-computer interaction. In order to do that, we need quite a large team. So we have about 30 people involved in this project. They are professors at URGS and PUC. I'm the principal investigator, and Marabel is the co-PI. In SEMPES Petrobras, we have a large group involving systems analysts, software engineers, and librarians. And then we have PhD candidates, MSc students, and also undergrad students. So here is an overview of what we are addressing. So we have the user who wants to search for figures and textual documents. And then in the middle, we have a multimodal information retrieval system. And then we want to provide results that have both text and images. So let's have a closer look into this process and into the components of our proposed system. On one side, we have the user with a query. On the other side, we have the figures and the textual documents. The search process is enabled by a search engine, which relies on a previously built index. Regarding the textual documents, a significant part of these documents is stored as PDF files. And before we can give the text to the search engine, we have to extract the text from the PDF. This sometimes may involve OCR and correction whenever there are errors. So here's the extraction and correction step and the plain text. Besides searching through the contents of the text, we also wish to enable search according to the type of the document. For example, if it's a report or if it's a contract. So in order to do that, we'll enrich metadata about the document, and that is going to be based on a document ontology. That metadata is what we give to the search engine. Regarding the figures, we also want to generate metadata that can be searched. In order to do that, we have a figure classification system which relies on a figure ontology which has already been developed in the scope of this project. Then, in order to retrieve more relevant documents and make the user happier, we are also working on automatic query expansion, which augments the user query and then tries to match more relevant documents. And automatic query expansion is done using a domain ontology and also models and word embeddings generated from in-domain corpora. Finally, the results are shown to the user, and we want the results and the query to be supported in a well-designed user interface. Now we're going to talk in greater detail about each of the components in this picture, and we'll start with the textual extraction and correction. The problem we have here is that extraction errors can have a negative impact on the quality of IR systems. And like I said before, the text from the PDF documents may need to go through OCR. And errors can be found even in mainstream search engines. This is a query I submitted last year to Google Scholar. And here we have what Google Scholar retrieved, and this is the actual PDF documents. We see here that some words have been divided into two, separated into two, and sometimes we have two words that are joined into one. The problem here is that a query has the correct spelling for these words. This query would not be able to retrieve this document, even if it's relevant to the query. So the types of errors besides separated and joined words, we have exchange of characters and erroneous symbols. We have done some experiments in which we systematically insert errors in a standard information retrieval test collection, and we found that if the word error rate is equal to or greater than 5%, that means a statistically significant loss in retrieval quality. And we have reported that on a paper we published earlier this year on the European Conference on Information Retrieval. The extraction and correction process typically has three steps: the extraction and OCR, and then we get a plain text. The plain text is sent to a filtering step, which will decide if the sentence has an error or if it doesn't. If it doesn't have an error, then it can go straight to the search engine. If it is found to have an error, then it needs to go through a correction step. And then what we are actually addressing here are steps 2 and 3. And our proposed solution is called Socrates, a system for correcting OCR errors. On step 2, which is sentence filtering, we are using a pre-trained BERT model fine-tuned to detect sentences with errors. And in step 3, we have a random forest classifier, which takes candidate corrections from spell checkers such as SimSpell and ASpell, and it also has format features from like height, length, and the case of the letters. And we also use syntactic features, which are customized to the task of recognizing OCR errors. We have done some experiments, and what we have here is a recall precision curve, which is a standard way of reporting experimental results in information retrieval. We have the red line here that represents the results of a set of queries on a data set that has errors, so before the corrections have been done. And the green line is the ideal. It's the same retrieves, the results for the same queries in a clean version of the text. What we are getting here so far is the blue line. You can see that we are closer to the green line than to the red line, but there's still some way to go. So it's still ongoing work. It's a very challenging task. We thought it would be easier when we started. And the thing that makes it difficult is that there's a balance between fixing errors and introducing errors in words that were correct. And the reason why we sometimes introduce errors is that we were not expecting that word there. It could be a very rare proper noun, and we don't have an exhaustive list of all the possible words in a text. And a bottleneck that we have is that experiments with real in-domain data require significant manual effort in creating an annotated data set. And we are not there yet. We don't have those resources just yet. Now let's go back to our picture and move on to the classification and metadata enrichment step. So we have a team from the area of information technology who are doing a thorough investigation on the types of documents, their provenance, their roles, and so on. They're using archival principles to build a functional classification hierarchy to represent provenance and documents in their production context. And then this information is what we are going to use to enrich the metadata of the textual documents. And in order to do that, they are relying on a collection of ontologies here. Going back to our picture, let's move on to the figure classification module. So our first step was to develop an ontology of figures. It is actually a domain ontology with a taxonomy of figures related to oil exploration. There are seismic images, maps, geological sketches, and so on. The ontology is composed of 139 classes that specialize existing ontologies, the information artifact ontology and the geocore ontology. This ontology was published last year in Ontobras. So we have the ontology, now we need the images that are going to be classified and be used as training data set. So we have collected quite a large set of images. It's almost 110,000 images. They were taken from different sources, theses and dissertations on the domain, public images we found on Google, some publications by Petrobras which are freely accessible, and data from previous projects. So far we have almost 9,000 annotated images that were labeled with our in-house tool, Label Web. We have 21,000 images that already came to us with non-known class annotations, and so that means we still have a large set that are yet to be annotated. One important remark here is that the quality of the annotation is as important as the quantity. So this is a screenshot of the annotation system that is being used by specialists to assign the expected label to a set of images. Now, to get the training data, we performed an automated expert-guided algorithmic filtering. On the first step, we have prioritized 46 of the 139 classes. We have ignored images with ambiguous annotations that happen when the annotators disagree on the actual class the image should belong to. And we are preserving only non-composite images. That means if someone has assembled a set of images into one figure, then we are discarding them by now. This way we have a clean data set for training. Now for the image classification. Well, it's still a small data set considering the number of classes, 46 classes. That means that a convolutional neural network trained from scratch performed very poorly. So instead, a better way is to do transfer learning. We take a pre-trained network from the ImageNet set. That network is able to recognize 1,000 classes, and it's been trained on 14 million images. That's quite a lot. Due to the small number of images per class that we have, we chose the MobileNet network as the base model because it has fewer parameters to be tuned. We designed a hierarchical classification model, which I'm going to describe next. So with the 27,000 annotated images we have a root classifier that is able to recognize 26 classes. And then we have two specialized classifiers, one to distinguish between the map classes and one to distinguish between the graph classes. And these percentages you see here are the classification quality measured in terms of F1. So 82% for the 26 classes recognized by the root classifier, 74% for maps, 87% for graphs. Those numbers are quite high if you consider that we have all those 46 classes. If we just did a random assignment, we would get just over 2%. So here are some examples of the classes that the root model is able to recognize. So we have 3D block diagrams, profiled, scan page, seismic sections. For the specialized models, the maps, reference maps, geological maps, geophysical maps, and so on. And for the graph models, if it's a bar chart, a line graph, and so on. So summing up on figure classification, we have quite an accurate model. We are still trying to improve the distinction between some difficult cases. For example, geological process sketch and schematic drawing are hard even for humans sometimes. So they are still not being told apart perfectly by our model. This system is under test phase, and it's soon to be released as a service internally at Petrobras. Moving on to word embeddings and language models. Natural language processing is an area that has been advancing enormously in the last few years. So our goal here is to make practical use of these advances and create, evaluate, and apply state-of-the-art NLP techniques. We have already taken part on the development of PetroVec, which are word embeddings in Portuguese on the oil and gas domain. We had a paper accepted at Computers in Industry, and it should be out very soon. And the resources we have developed for that work are publicly available on this GitHub repository. Moving on from that, the next step is to train a BERT model on the oil and gas domain in Portuguese. So BERT is a recent NLP model which has been getting state-of-the-art results in a number of NLP tasks. Once we have the pre-trained model, we'll use it for re-ranking search results, to help us fix OCR errors, and also for named entity recognition, among some other tasks. Now, the automatic query expansion model. This specific part, has been conducted mostly by our partners in Sempes Petrobras. So here on the left, we have a typical common query. So the user issues a query, and then the keywords that are used in the query are matched against the index in the search engine, and then these results here, this small branch, is retrieved. When you have an expanded query, which was generated by automatic query expansion, then the original keywords are augmented with related words, synonyms, and so on that may come from a knowledge organization system. And the idea is that this augmented query is going to be able to retrieve the whole tree here, so further relevant documents. So we're still, this is still under work. We hope to be able to use the word embeddings and the BERT models to enrich this process too. We are also concerned with the user experience and how to design a good interface. So moving on to that, on the search interface, it should be properly designed and optimized so that it can be a powerful portal that connects users to their needs, even to needs that the users are yet to discover. A well-designed search interface is a great way to help users stay engaged and easily find what they are looking for. Though today most sites have a search bar, many don't provide a holistic search experience. They don't provide advanced searches. They don't let you navigate within the results. So we believe that great search extends beyond the search bar to include further functionalities. In order to do that, there are some steps to follow. First, we need to know the user. So we are conducting user studies, interviews, questionnaires. We are defining tasks and goals. Enterprise search is different from internet search. We believe recall tends to be more important in enterprise search than it is in internet search. And there's also confidentiality issues in a company. Then we are going to build prototypes to explore and validate design ideas, evaluate first without the users and then with the users, and iterate. This is a cyclic process, so we'll have to repeat this a few times. Also under development, we have an in-domain test collection for information retrieval. A typical test collection for information retrieval includes documents. In our case, we'll also have to have images. And there's a set of queries that is necessary. And these queries should try and simulate the actual queries that a user would pose in that document collection. And then we have the expensive component of a test collection, which are the relevance judgments. The relevance judgments require humans to manually assign for the queries which documents and images are relevant. So this is still ongoing. We are also exploring different alternatives for multimodal information retrieval. So besides doing the search on metadata, we want to explore training a neural network that will be able to map high-level textual and visual features into the same vector space. So the idea is to have in the same space images and text, and see how we can do on that. So for next steps, we still have a few months to go until the end of the project. In these months, we need to put the pieces of the puzzle together. We need to combine the components that we have been developing in parallel into a cohesive integrated solution. So we still have to assemble this puzzle. So that's all for me. Feel free to email me if you have any questions on this topic. Thank you.